Case Western Reserve University's Institute for the Science of Origins proudly presents the Origin Science Scholars Program. The Institute advances the scientific understanding and application of origins and evolution of human and natural systems. The Origin Science Scholars Lectures are presented with the assistance of Case Western Reserve University's Siegel Lifelong Learning Program, College of Arts and Sciences, and Media Vision. Tonight, it's my pleasure to present Roberto Fernandez Galan, who is Assistant Professor in Electrical Engineering and Computer Science at Case Western Reserve University. He earned his PhD in Computational Neuroscience from Humboldt Universität in Berlin and did postdoctoral research in electrophysiology and computational neuroscience at Carnegie Mellon University. And tonight, he'll be telling us about making sense out of noise in brain circuits. Please join me in welcoming Professor Galan.
Thank you very much, Glenn. It's a great pleasure for me to be here and to have this opportunity to talk to you about my research. I really love events like this. I think they help revamp academic life, in today's times, which are not optimal for science. So I think this is great, and I would like to start by thanking everyone who made this possible. Patricia Brinshaus, Glenn Starkman, Jay Mann, and Ken Loparo. So. Of course, on the Emerita Academy. Thank you very much. Well, thank you for coming. I'm going to talk about noise in the brain. I'm going to define what noise is in biology and what it does. I'm going to show that there are some similarities with electrical circuits. Most electrical circuits, all of them virtually have noise, and that noise is typically a nuisance, is a distortion or a perturbation to their function. The same happens in brain circuits, but there are two main differences. The first one is that the noise is much larger, okay? So brain circuits have evolved to actually take advantage of it and make some functional use of noise. And that's what I'm gonna be talking about today. I'm gonna be talking about what biological noise is, how it is defined, how we can manipulate it or model it, and then what it means at the functional level, at the level of small brain circuits, and as well, and also at the level of systems biology, if you will. So if there is an aphorism that summarizes what I'm going to tell you today, is this one by Heraclitus of Ephesus, that no man steps twice in the same river. Okay? I think that describes very well what the brain does in general. So when you present a stimulus to the brain, the brain is going to react to it, but if you present it several times, every single time the brain is going to be in a different state. Okay? So now the question is, how is that going to affect your perception of the stimulus, and what does it mean that the brain is not in the same state twice? So, the analogy of the brain would be the river, that, the water is flowing all the time. So even if you present the same stimulus twice, even if you step twice in the same river, the brain is going to be in a very different state. Okay? So people have known that actually for a while, since the beginning of neuroscience, when they were making measurements of electrical activity in the brain. For example, in the auditory cortex, if you put an electrode on your scalp, you don't need to go invasive. You just put an electrode outside, and you just record ongoing activity. What you're going to see is something like what we see here, that there are like 10 repetitions or 10 segments of 1 second duration, and they fluctuate. Okay, so there is some background electrical activity going on, which is good because that means that you're alive. Okay. But that happens spontaneously, okay? Now, if you do present a stimulus, the very same stimulus, in this case an auditory stimulus, a click, what you see is that, wow, something happens, the electrical activity changes, but it doesn't do it very consistently. So you have here 10 different repetitions of the same stimulus, and what you see is that, the baseline goes down and then goes back up. But there is a lot of variability. Now, you can average all those responses to get like, basically a consistent deflection, a consistent response. And that's done, and that has been done for many years in neuroscience, and that's what many neuroscientists have been focusing on, which is this is response to the stimulus. But obviously, it's not. Right? It is the average response to the stimulus. Every single realization of the stimulus is going to be accompanied by some background activity. So now the question is, one, where does the background activity come from? Two, does it have any functional role? So again, I'm going to address those two questions in the rest of my talk. Okay? But to do that, we need first to learn a little bit about how the brain is made up. And it is made up of cells. No surprise there, right? This is a neuron, which is the cell of the brain. They have electrical activity. They fire electrical discharges. And they communicate with one another by basically passing the electrical activity from one to the other. So if you look at this picture, the cell, the body of the cell is right there, and these cells are in your cortex, in the very close to the surface of your brain, actually. And you also see that they have like many different branches or dendrites, and those dendrites are sampling the electrical activity of their neighbors, and actually they integrate that activity. So if there are like many neighbors that are activated, then this cell will be activated and it will fire an electrical discharge. And that electrical discharge will propagate to other neurons, okay, to other cells. So the 2 points that I want to make here is, one, that the neuron is not isolated. And the other one is that, because it's not isolated, it relays information to other cells. Now, let's talk now about going back a little bit to the noise concept. So if you take the cell that I showed you before and you inject an electric current to stimulate it, what the textbook says is that what you should see is basically like electrical discharges that are like a clock. Okay, so you inject a current and then you should see like a very regular pattern of electrical discharges by that neuron. That's not exactly what you see if you go to the lab and record the electrical activity from one cell while you stimulate it. Yeah, on average, across different realizations of the same stimulus, you're going to get the same number of electrical discharges or spikes, which are like these spikes that I'm showing you. But in every different realization, the timing of those spikes is going to be different. The reason for that is that there is some background noise already at the single cell level. So what I was showing you before is actually noise or variability at the level of the whole brain, which you can record with one electrode on the scalp. Okay? This is already variability and noise at the microscopic level of a single cell. The cell is not a clock, which is what you would presume if if noise was not there. It has a lot of variability and flickering in its response. So now, what's causing that noise? So for that, I want to give you like a general introduction first about what is the origin of noise in any physical system. And for that, probably you will remember the concept of Brownian motion or thermal noise. You have a physical system like, a very simple one, a container with gas or a liquid. And the molecules of the liquid or the gas are actually, they don't stay put, right? I mean, they are moving around and they are vibrating. Those vibrations, the energy of those vibrations come from temperature. That substance is at a given temperature. What that means is that the temperature is the kinetic energy of the molecules around their equilibrium, right? So they are going to be moving around. And Robert Brown, a botanist, he measured that experimentally when he was investigating under the microscope grains of pollen. And he realized that, the pollen, when it's floating in water, it follows like a very random trajectory. So, he named it, or people named it after him, Brownian motion, because he described it physically. He didn't provide a mechanistic explanation. for this phenomenon. That was elaborated later by several big names in physics like Einstein, Paul Langevin, and Onsager, another physicist. They described the phenomenon that Brown discovered and provided an explanation in terms of molecules. Okay? Back then, the people were developing the atomic model of matter, and you needed some knowledge of statistical mechanics and things like that to quantify those phenomena, and eventually they were, okay? But the bottom line is that the particles, due to their own energy, the particles of the gas or the liquid, are fluctuating. They don't stay put, they fluctuate. So that happens also with static noise in the old radios and even in the new radios as well. You have some noise in the system. Where does it come from? Where there are two sources of noise. One is the background electromagnetic radiation, which is, it's not always perfectly tuned. There is some background noise at the level of the antenna, if you will. But most of the noise actually in old radios is coming from the circuits themselves. So Brownian motion also applies to metals and the atomic lattices of metals, where the ions vibrate due to thermal temperature or due to temperature, and that causes collisions with electrons. Okay, so that's the mechanistic explanation for resistance. Okay, and the resistance is the origin of noise at the molecular level in conductors. Okay, so the same idea of things that vibrate on a microscopic scale explains these two phenomena. Okay, it also explains the kind of noise that generates variability of responses in the cells that I was referring to before. So what I'm showing here is a patch of the membrane of a neuron. And I was telling you before that neurons fire electrical discharges. Those discharges are caused by current, by ions, charged ions, flowing through pores in the membrane, through ion channels. So the more channels are open, the stronger the current. Okay? So the interesting thing is that, again, this is on a microscopic scale. What that means is that the cells or the molecules in the membrane are moving around, they are a little bit jittery, they are fluctuating, and those fluctuations translate to the channels, to the pores themselves. So in addition to the stream of ions that cause the electrical discharge, you're going to have some random opening and closing of those elements. And that's going to create noise in the electrical patterns that the cells create. The important idea to keep in mind here from this representation is that the mean current that causes the electrical discharge scales linearly with the number of channels. The more channels are opened, the stronger is going to be the current that flows through the membrane, so the stronger the electrical discharge that they will make. But the current fluctuations due to Brownian motion of the ion channels in the membrane, they scale like the square root of the number of channels. That's very important, because what that tells us is that the noise, the fluctuations of the current relative to the mean goes like 1 over the square root of n. So if you have a large number of ion channels, of pores, you can neglect the effect of physiological noise. It will vanish. The fluctuations relative to the mean become more and more negligible. That's important because people who do experiments in the lab, electrophysiologists, have noticed that young cells that you culture, they fire very randomly. Whereas cells that are mature, neurons that are mature, they fire more like clocks. So that's what basically what that's telling us, and that's known. Mature cells have more channels than younger cells. Okay? So this applies also to the concept of synapses. The electrical discharges between neurons are not propagated by electric fields. They are propagated by chemical messengers or neurotransmitters. And those neurotransmitters are packed in vesicles. When one cell fires an electrical discharge, all the synapses, all the connections to other cells are going to release neurotransmitters. Now, the statistics of that process is very similar again to Brownian motion or the noise that you have in ion channels. The mean current of neurotransmitter between cells is proportional to the number of vesicles, whereas the fluctuations due to random collisions of those vesicles with the membrane scale like the square root of n. Okay? So what that means is that if you have big synapses with a lot of vesicles, the fluctuations, the random release of neurotransmitter is going to be negligible. But if you have small synapses, you're going to have synaptic currents that are going to be very noisy. Okay, so this is the take-home idea about the mechanisms for physiological noise. Numbers do matter. If you have small connection, if you have small synapses, small connections between neurons, they are going to be unreliable. They are going to be noisy. And if you have a lot of ion channels, then you're going to have a more reliable neuron.
MEG, magnetoencephalography, is going to measure the mean of a larger surface area than your EEG. And I'm just wondering if anybody has integrated the two systems yet.
I'm going to give you an example. I have to speed up a little bit, but I will give you an example of noise at the whole level, at the whole brain level. And that has been estimated with MEG rather than EEG.
This is a small question. What do you mean by an unreliable neuron?
Unreliable would be that, you know, it doesn't respond the same way to the same stimulus, right? So that's basically the concept, yeah. So you cannot predict accurately its response even if you present the same stimulus several times.
Thank you for joining us. You have been watching Dr. Roberto Galan discussing the noise found in the human brain and other biological systems. For more information on the Origin Science Scholars Program, please visit the Institute's website at origins.case.edu. In the next part of the talk, Dr. Galan will discuss how neural circuits make use of that noise. Now, back to the talk.
What I'm showing you here is actually an example of synaptic noise. Okay, you can record the currents, the synaptic currents that travel from one neuron to another. And basically what I'm showing you here is like, you know, pulses. Those pulses look very random, and they occur spontaneously. And you know, that's what you would see in the baseline. Now, can we manipulate this? So we found a way with my students, one of them is sitting here with me, Nathan Kodama. We found a way to actually control or manipulate the level of noise. When we presented a drug that happens to be an antidepressant, what we discovered is that that kind of, you know, synaptic currents become wild, very noisy. They are still very random, but very large. Moreover, what we showed was that the noise increases so much that in vivo it generates epileptic seizures. Now the question is, can you block them? We found a way to block them, and you know, with another drug that I'm showing there. Okay, but this is actually an exception. Synaptic noise or channel noise are not really manipulable. It's very difficult to control them in an experimental setting. That's the reason why you have to resort to computational analysis. You have to run simulations of circuits and neurons and evaluate what the noise makes to them. Now, simulating biological noise, the mathematical underpinning for it has been known for a while, for about 4 decades. But it's known to be extremely inefficient computationally. So with one of my students, we found a way actually to speed up the computations that involve noise. And suddenly that was a big milestone for us, because then it opened up the possibility to explore the role of noise in many different contexts. Okay? And that's basically what I'm going to tell you about in the second part of my talk. This was supposed to be the slide where I would take questions. So here what I'm showing is traces electrical discharges, spikes, from a real neuron. And what we see here is a computational model that incorporates biological noise, the one that I was describing before. So you see that they are very similar. There are also some differences. Those differences are actually mechanical perturbations that you don't have in the computational model. But overall, it's very accurate. And importantly for us as researchers is that it is very efficient. So now we can really play around with them. So the first example that we did to use this technology, or this approach, was to investigate a minimalist circuit that is everywhere in your brain. That's called feed-forward inhibition. And basically, it consists of a neuron. In this case, information is traveling from the left to the right. So this neuron fires, and then this one is going to fire as well. But you have another parallel pathway here with an inhibitory neuron that is going to try to suppress the firing of that cell. For some reason, this motif, this circuit motif, is everywhere in your brain, in the cortex, in the hippocampus, even in the cerebellum. People have several ideas about what it means. We don't know exactly what it does, but what we can do is investigate it within our framework, and considering two parameters here. One is the delay that we have in the inhibitory input relative to the excitatory one. The other one is the duration of the synaptic pulses between the neurons. I don't want to get too technical. I'm just going to give you the gist of it. All I want to show is the following idea. When you have some background noise like the one that I was telling you, that's going to affect the way in which this mini circuit can transfer information or generate information. Not generate, but really transmit information. So you can do that. You can quantify it. I'm not going to get, again, into any technical details, but I'm using tools of information theory, which basically tells you whatever this neuron here is encoding, okay, when I present a stimulus, it's going to be subject to noise. If that neuron is driven just by noise, in different trials, I'm going to get very different patterns. Now, if it's not driven by noise, if it's driven by the previous neuron, those patterns are going to be much more consistent. In information theory, we know that if you compare the order, in these cases, the reliability of the responses in these trials, versus the unreliability over these trials, you can compute the information transfer. You can compute whether, how much information that circuit can actually encode. So in a nutshell, what I'm showing here is this is the information that you can encode as a function of the duration of the synaptic pulses. Why am I interested in this? This is the parameter that you can manipulate with drugs, with pharmacology. Okay? So typically, drugs are going to make the synaptic communication faster or slower. But the bottom line is that depending on the two parameters that I was alluding to, the duration of the pulses and the delay between excitation and inhibition, you are going to get like different lines there. And in particular, I'm interested in the green one because I know that this is not physiological. In that range, neurons are firing not in a physiological range. They are firing a lot. So, biological systems are going to avoid that because, it would take a lot of energy from them. And the blue line corresponds to very little firing. So the green line is really the target. That's the level of activity that neurons tend to have in vivo. And if we pay attention to that curve, what we see is that there is an optimal duration of synaptic pulses in the presence of noise to encode information. Okay? So let me back up. There was a lot of information here, no pun intended. The idea is that the circuit that I presented, it's very common, and it's subject to noise. The question is, in the presence of the noise that I was describing before, how much information can it encode? The answer is, it critically depends on how, what the duration of the synaptic pulses is, and what the delay of the loop that I showed you is. Okay, and that's so by tweaking those parameters, you can overcome the limitations of having background noise, which, as you may imagine, always tends to deteriorate information transfer. So the next example, it's actually the circuit that I was showing you is really a minimalist one. Now we can try to investigate something that is more relevant from a systems biology perspective, which is the circuit that you have in your brainstem that controls your respiration. Okay? Work by other people have convincingly shown that this small circuit, that circuit can mimic all the process of controlling your diaphragm and therefore your respiration. But nobody has investigated what the effect of having intrinsic noise in that circuit is. Okay? So we used that model, that circuit model, and we simulated it first to verify that we can see patterns here that mimic respiration. In particular, I want you to focus on the pre-eye neurons. The pattern of activity of those neurons go up, goes down, correlates strongly with your diaphragm. So when pre-eye is up, you tend to inspire. I mean, you do inspire. When it's down, you expire. Okay? So, but again, the phase of inspiration and expiration is going to be affected by the structure of the circuit and the presence of background noise. Okay? So if you ran those simulations, then you can show that depending on the number of ion channels, which is basically the parameter that controls the noise, depending on what that number is, you might have slow to normal breathing. For the physiologists, I don't know if there are like physiologists in the audience, but that is a very realistically looking breathing pattern. Again, when it goes up, that means inspiration, and expiration is the flat part at the bottom. Inspiration is shorter, expiration is longer. Now, if we increase the number of ion channels in that circuit, which basically is equivalent to decreasing the noise, then what you have is that different pattern of respiration. Okay, it's much faster, and you change the duration of inspiration relative to expiration. And if you increase it much more, what you have is apneusis, basically jagged breathing. Okay? And that's just controlled by the total level of noise that the neurons can support. Now, is that realistic? So I was telling you before that immature neurons tend to have fewer channels, and that creates more variability in their responses, and that makes them a little bit more unreliable. So newborns tend to have very irregular breathing patterns, and that's a problem because they tend to have very long expiration periods. And over those periods, they can suffocate, basically. So it is very important to keep track of how newborns, and especially if they are premature, are breathing, because they could asphyxiate if they don't breathe fast enough. Now, the mechanisms for that irregular breathing at that young age are not completely known. People think that neuromodulatory inputs are immature, but I think there is a more parsimonious explanation of why premature babies breathe so irregularly. And it's that they have alternating patterns of very fast breathing, very slow breathing. And that's exactly what you would expect when you don't have enough ion channels and synapses in your circuit, because you have an immature circuit, and that's going to create unreliable breathing patterns. Now, that doesn't mean that that's necessarily bad. It's only bad if the expiration period is long enough so that you asphyxiate. Okay, but we have an explanation based on this model for what happens to premature babies. In terms of the variability of breathing and what a potential mechanism for that is. So The other example that I want to talk about is actually at the level of the whole brain. And that's based on a paper that I published a long time ago. It was my first paper as a faculty member at Case, which is that you can use actually noise on a macroscopic level to infer how different parts of the brain interact with each other. What I showed in that paper is that if you assume, as I'm doing here, and I'm pretty convinced that that's true, that biological noise is the driving force of spontaneous neural activity. So if we say the noise is there, we cannot get rid of it, but we can take advantage of it to investigate how neurons or different brain areas are connected with each other. That's because all the randomness that you have in the noise, it's going to be constrained by how neurons are wired together. So that's fairly intuitive because if this part of your brain gets activated spontaneously, and you see that this other part of your brain always is activated right after, regardless of how random the activity looks to you, that causality or that kind of correlation suggests that there is some causality. So you can use actually random, noisy brain activity to infer how brain circuits are wired. And that's what we did. The key underlying idea is that if you focus just on resting state activity of the brain, so you are not stimulating your brain intensively, you are just quiet, relaxed, you are not listening to music, you are not exploring anything with your eyes, then you have like resting state activity. And you might consider that what is going on in your brain, your mind wandering, might be a reflection of noise, okay? If you will. That might be a little bit of a simplification, but let's bear with me here in the argument. So the interesting thing is that at rest, any physical system close to an equilibrium can be modeled, can be mapped onto a model like this one, where you have an output, you have a black box, and you have an input in open loop. Okay, so that would be like the engineer's view of a system that is close to rest. Okay, the output is what you measure, let's say your EEG or your MEG, and if you fit your data, your output, if you fit this, which is what you know, to this model, what you can retrieve is some parameters of the brain of that black box, which we are not going to be concerned about. People would refer to that as functional connectivity between different brain areas. You can measure the input, which would be the driving force of brain activity, the noise. So basically, think of this as electrodes on your scalp and the activity that you measure with those electrodes. If you use those signals that you record and feed them to this model, you can infer what the noise, the input, the drive that generated those activity patterns was. So if you do that, in particular with MEG signals, you can map the spatial pattern of noise. Okay? So in this particular case, red would be very intense activity of noise, blue would be not so much intense. Each of those circles represent a head for a different subject, and that would be like the map of activity of noise on the scalp. Now, these are some subjects, control subjects. I have another testing condition there. And I would like to query the audience whether they are able to distinguish the features between those two groups. Are there any features that pop up to your eyes? Which one is more regular? The one at the bottom looks much more regular. And that's what we realized. And you can use measures of regularity to test that. And indeed, we see that one group, which is control subjects, on average is more regular than the autism spectrum disorder. Those were two groups of children. One were control children. The other one was age-matched children that had high-functioning autism. So that shows us that noise can actually be used as a biomarker. It's a small group, it's a small study, but it's a proof of principle that noise at the large scale level of your brain is relevant, at least as a biomarker, if not about the physiology.
So you said you chose high-functioning autistic spectrum disorder children. Do you expect, or did you ever do low-functioning autistic children? Would it be different, or is it different?
The answer is we don't know. It was not really my choice. I presented my approach to some colleagues in Toronto, and they told me, we have data that we have already collected where you could test this. But these are the constraints. We cannot add more patients, okay? And the population of children with autism is very homogeneous, okay? They are only, what was called before Asperger, okay? So they had the diagnosis at Sick Kids Hospital in Toronto, Sick Kids, which is a very big hospital for children. So the data were already collected. I've tried to, collaborate with other people and extend these studies, but, I'm not there yet. Okay.
Can you comment on comatose patients?
I don't have the data, so it's really difficult for me to speculate what you would observe there. There are some studies already there that actually from some of my colleagues in Toronto as well, where they observed different patterns of brain activity. I can tell you that during sleep, shallow sleep or deep sleep, we have found, that's an unrelated study, we have found very specific activity patterns, which happen to be spherical waves of electrical activity. I'm relating this to your question because, people have noticed that the low frequency activity that you observe during deep sleep is actually very similar to the one that you observe in many patients with coma, in coma. Okay, so that's all I can say. I don't have the data, and I haven't tested it.
You mentioned the use of medication. What is it that you would use medication for?
The goal is actually not to use this as a guidance for drug development or anything like that. But what I was referring to is, let me go back to that slide. Let's say that you are in this regime, okay, that the parameters of your circuit basically are described by the green curve, okay? So the duration of the synaptic pulses is this parameter, tau. Now, if you think about, for example, pills that people take to go to sleep, like benzodiazepines, or they are also treated or used to treat epilepsy to some degree, what they are doing is they are lengthening the duration of synaptic transmission. So what you would do is you would shift for a 4 millisecond duration of synaptic pulses to, let's say, an 8 millisecond duration. When you do that, your ability to transfer information in your circuits drops by half. And incidentally, when you take benzodiazepines, then you get a little bit groggy, people say, right? And eventually you fall asleep. It's not that your brain is basically less active. It's that your performance also deteriorates, and you cannot drive or use heavy machines with it. Perhaps that has something to do with the fact that your ability to transmit information from different circuits in your brain is dramatically attenuated. So thank you for your question, because that's the idea that I wanted to convey, and perhaps it was not, it was buried in all the technicalities.
We hope you've been enjoying the Origin Science Scholars Program with Dr. Roberto Galan. Dr. Galan is an assistant professor in the Department of Electrical Engineering and Computer Science at Case Western Reserve University. In the second part of our talk, we learned how brain circuitry might exploit noise. In our final segment, Dr. Galan will talk about the concept of criticality, how the brain balances between two states in order to better exploit noise. Now, back to our talk.
Now I want to zoom out a little bit and get a little bit more philosophical and perhaps less technical, which is this idea about, does noise matter? So if we go back to the problem of Brownian motion, or the phenomenon of Brownian motion of molecules, we know that in some situations Brownian motion can be critical, in some other it's not critical at all. So if you have a piece of ice, basically iced water, at minus 20 Celsius, obviously you're going to have thermal fluctuations, right? So the water molecules in the ice crystal are going to vibrate a little bit, but those vibrations are going to be inconsequential. Now, if you bring the temperature close to the melting point, then the random fluctuations of the molecules and the vibrations some of them might be strong enough to start breaking the glass apart, the crystal apart, and then is when you have melting water. So, you could argue the noise that I'm showing you at the microscopic level, does it matter? Does it propagate to the macroscopic level? And can it change anything? Well, if you are around a critical point, it should propagate and scale up. And I just showed you an example where, that variability at the global level, it might be significant. And obviously, if you bring, in water in particular, you have the triple point, where if you tune your sample at that point, random fluctuations of, vibrations in the, at the molecular level can, make you coexist, or, the sample will coexist as water, gas, and solid. I mean, there are awesome videos on YouTube. Unfortunately, I didn't see that when I was a student in the lab, but now on YouTube you can find everything, obviously. And there are beautiful examples of the triple point where you really see that, those three things can coexist because you are close to criticality. Now, people have speculated for a long time that the brain is on the verge of criticality, of a phase transition, of a critical point between, normal thinking and falling asleep, or normal thinking and an epileptic seizure. And there is some evidence already, but it's not an easy problem to address. First of all, because the phase transitions that you have in water or other substances really don't reflect the complexity of biological systems. However, in biology and in chemistry, you do find phase transitions that are far away from equilibrium. So in systems where you have strong dissipation and waste of energy or use of energy, you can also have phase transitions that are analog to the ones that you see in thermodynamics, for example. So I want to show you just two examples of that. One celebrated model is the reaction diffusion equations that can generate complex patterns. And that would be when you are close to a transition, to a tipping point that supports complexity, okay? And people have investigated the role of noise or, small fluctuations around that. And, the intrinsic Brownian motion of the molecules in those reactions can increase the complexity of the patterns that, the chemical reactions display. So in different colors, basically, you have like different molecules that are reacting with each other, and at the same time, they diffuse their products. And you can have more abstract systems, even binary systems that, are just black and white cells interacting locally with each other that display also complex patterns. So this is basically what it's called a cellular automaton. What you have is that the dots, the black dots that you see there, interact with their neighbors. And the interactions are very simple, but when you iterate them for all the black points, you generate a lot of complexity, okay? So there is this idea or this hypothesis that, the circuitry of the brain is close to a transition between different states, and that fluctuations can actually exacerbate the complexity that you can display. I'm going to stay just at the analogy level. I'm not, because there's no mathematical proof whatsoever, but I just want to convey the idea that it's floating in the community in neuroscience that the brain is a system at criticality, isn't on the verge of suffering a phase transition, that it's not like those in thermodynamics, it's more like the ones that you observe in these other chemical systems, or the complexity patterns that you can develop with abstracted reaction diffusion in these cellular automata. So now the idea is, what are the tests? How can we test this idea that is out there that brain circuits or the brain as a whole is a system close to criticality? Do they really operate at criticality? So that's a very difficult thing to test in general. And again, there is already some evidence there from other labs. And I'm going to show you evidence from my own lab. This is very preliminary what I'm going to show you. These are studies that I've been doing with one of my students, Nathan again, who is here in the audience. I'm going to show you two pieces of evidence that the brain is a critical system, is on the verge of transitioning between multiple states. What I'm showing you here is the preparation that probably, we don't need to get into the details there, but basically this is a brain slice, okay, from a mouse. And what we place on top of it is an array of electrodes. So each of those electrodes can record the activity, the spontaneous ongoing activity, noise-driven activity, if you will, by several neurons. But you can identify them just by looking at the shape of their electrical discharges. Okay, that's called spike sorting technically. The really important part is what I'm showing you here below. Each of those lines, black lines that you see, are electrical discharges, and every row is a different neuron. So we can record from around 300 neurons at the same time over time. And if you look at it, it looks very random, very noisy, very unpredictable. But there is a lot of structure here in these patterns of electrical discharges over time. So I'm going to give you the two features that are consistent with the brain being a system at criticality. The first one is what it's called fluctuation scaling, which basically means that neurons that are slower in terms of firing, they tend to be noisier. Okay? So neurons that are slower, they are less reliable in firing. What I'm plotting here in the x-axis is the mean interspike interval. So when this is high, it means that you have slow neurons. And here is the variability of those electrical discharges. Okay? So slow neurons, sorry, let me, I know that you don't see the pointer. Slow neurons fire more irregularly. Okay? So this is a prediction from having a system close to criticality. The fluctuations, the noise, scales like the mean, in this case the mean discharges. Okay? So that's one piece of information. The other one is this one, which is self-similarity. These tiny circuits, which are about 1 millimeter squared, they display the same rhythms and the same electrical patterns that you can record in the whole brain with MEG or EEG. Every peak that you see here corresponds to one of the bands that people talk about, like the theta rhythm, the alpha rhythm, the beta rhythm. So there is some self-similarity that brain microcircuits on a microscopic scale, they have similar activity to those that you observe on a large scale macroscopically. So these are really the two pieces. And what we know from the mathematical studies or in physics, about systems that are at criticality is that they can generate complexity. They can generate complex patterns in time, in space, and it's tempting to think that consciousness or our mind work is actually an epiphenomenon, if you will, of an emergent property of the brain circuits being close to criticality. Now that might sound far-fetched, and it possibly is. I think it's also very reductionist. It's basically telling us that our consciousness is just that. Our soul, our mind, is just an epiphenomenon of brain circuits. I don't want to go that far, and I have some problems with that interpretation. But there's no question that systems that are close to criticality can generate information, can generate new information from noise. Okay, the proof for that is way beyond this discussion, but it is important to notice, similarly, that what happens with water, that noise at the critical point is very relevant because it's going to determine whether you have water or ice. When the brain is at criticality, it can also, the fluctuations that it generates naturally, they can scale up to create information, and perhaps to some degree, that's what our minds are doing. Now, the summary of my talk is that noise is present in all brain circuits. It is also in electric circuits, but it's more pervasive and more intense in brain circuits. It is functionally relevant, not a nuisance. It's something that, during evolution, you have to factor that in if you want to improve the performance of brain circuits. And the other one is that brain circuits likely operate at criticality to create information from noise. Now, again, I don't want to sound too reductionist, okay? And I think that there are some perhaps contradictions with perhaps quantum mechanics, where you need an observer to determine the state of matter. For example, the electron in an atom. What we learned in quantum mechanics from Schrödinger and all these people was that someone has to take a measurement to know whether the system is in this particular state or that other state. So it seems that it is the observer or the conscious observer what really determines a property of matter. Now here we have the opposite situation where it seems that consciousness emerges from matter, or properties of matter, like the ones that I described, noise and criticality. It's obviously an open question. I don't have an answer for that. But maybe we can spark a discussion about those things and relate that to the mind-body problem. So that's all I have to say. Thank you.
The Origin Science Scholars Lectures are presented by Case Western Reserve University's Institute for the Science of Origins, with the assistance of the Siegel Lifelong Learning Program, the College of Arts and Sciences, and MediaVision. For more information on the Origin Science Scholars Program, including a full video archive, please visit the Institute's website at origins.case.edu.